think I'll get started. Good afternoon, everyone. I'm Mansi Shah from the Bureau of Research, and I want to thank you for joining us today for this Lunchtime Tech Talk webinar. Today's Tech Talk is one of a series sponsored by the NJDOT Bureau of Research that include webinars, lunchtime talks, and other events. The purpose of our Tech Talks is to share and promote the implementation of research and innovative practices and the transfer of knowledge among NJDOT staff and others within New Jersey's transportation industry. Today's Tech Talk provides an opportunity for NJDOT employees and others in the transportation community to learn more about the broad scope of academic research initiatives underway in our state. Today, we will hear from two civil and environmental engineering researchers who are associate professors at the New Jersey Institute of Technology. Professors Matthew Bandelt and Matthew Adams will discuss their research on advanced reinforced concrete materials for transportation, such as concrete materials with high ductility. Our presenters will share how these new materials have been developed to improve the service life of reinforced concrete transportation infrastructure. Now I'd like to introduce our moderator today, Omid Sarmad. Omid is a member of the Technology Transfer Team and the Local Technical Assistance Program. Omid will further introduce today's speakers and moderate the Q&A. Thanks, and I hope you enjoy the presentations.
Thank you very much, Mansi, and welcome everybody. Today's Tech Talk is going to feature presentations from two NJIT research professors, Dr. Matthew Bandelt and Dr. Matthew Adams. Dr. Bandelt and Adams will speak together for about 50 minutes today. And before we get started, we just want to go over some ground rules. If you want to submit a question, please use the bottom right-hand chat box marked Q&A. Please submit all questions to the host. We'll save the questions for the end and ask them during the Q&A. Professional development credits are available if you stay for the full session, and your name must be included among those who register today to receive credit. Also, please complete a feedback form that will pop up after the event ends, and we'll try to close out the event by about 1:15. Now, please let me introduce our two speakers. Professor Bandelt joined NJIT in July 2015 after completing his Ph.D. at Stanford University. Currently, he's an associate professor of civil engineering and associate dean for research and graduate studies in the Newark College of Engineering. His background and experience are in the behavior and modeling of ductile cement-based materials, performance of recycled aggregate concrete, and durability of reinforced concrete structures. Professor Adams is an associate professor and co-director of the Materials and Structures Lab at NJIT. His research focuses on sustainability, resiliency, and long-term durability of innovative cement-based materials. He also studies how governmental policy both support and hinder the adoption of sustainable practices in construction. So without further ado, I'll turn it over to Drs. Bandelt and Adams for our presentation.
Thank you. And we'll share the screen. Okay, and I assume you can see my screen. So hello, everyone. My name is Matt Bandelt. As was previously mentioned, I'm a faculty member at New Jersey Institute of Technology. Together with my colleague, Matt Adams, we'll be presenting on a recent project that recently finished up that was supported by the New Jersey Department of Transportation, as well as some companion work that we've done on a number of other related projects. The project that we'll talk about today, we also worked with faculty from Rutgers University, Professors Hao Wang and Hussein Najm, as well as Andrew Bechtel from TCNJ. Although the work that they were involved with isn't presented there, we recognize their collaboration. And specifically, we also recognize our two former students who recently graduated, both of which, Dr. Shurka Shitty and Jin Fan, who recently graduated and did a lot of the experimental and computational work that we'll be talking about today. So first, let me briefly just tell you a little bit about ourselves. I'll let my colleague Matt Adams just introduce himself for a moment here so that you know who we are. So Matt, go ahead.
Yeah, hi. Thanks for having us, everybody. So, you know, the bio read earlier says most of it, but really mostly I focus on the chemical and mechanical characterization of infrastructure materials. So I'm really more of a materials engineer looking at how Specifically, new concrete materials can be applied best in the field. And I do a lot of work with accelerated laboratory testing to understand how those test methods can best be used. And I've also gotten into working in the policy space to understand how we can craft good policies that will help support the use of resilient and sustainable materials without hindering their sort of application based off of older ideas.
Thanks, Matt. And for myself, my background is primarily in sort of structural modeling of new construction materials. And I do that both through experimental testing as well as computational methods as well. And our laboratory is located at New Jersey Institute of Technology. We have quite a bit of physical laboratory space where we'll do physical testing of construction materials and structural systems. We have an advanced analytical space as well, where we do material characterization work that we can then look at concrete and similar type construction materials under the microscope and do some advanced analytical work with that. And then we have some additional space where we do basic mortar testing and mechanical properties of different systems. So this is just a brief overview of our laboratory. The outline for today's talk, first what we'll do is we'll give you a background, a little bit of motivation and background on this project. Matt will then present the next two areas in terms of the experimental program and the results of the study. And then I'll accompany that with some numerical modeling that we've done that showcases some of the long-term durability of the materials that we studied in this project. And then we'll move on to conclusions and future work. So in terms of motivation and background, obviously, if you work in the transportation sector and specifically with concrete, you're familiar with some of the durability issues that concrete materials face, predominantly corrosion, shrinkage, salt scaling, freeze thaw, amongst a number of others. But these are, a range of durability issues that we face, especially here in the Northeast, due to the local climate that we have, the large scale of these materials that we use, the way we have to treat them, et cetera. And all of these durability issues are in one form or another due to some sort of deterioration mechanism. So if we think about drying shrinkage, for example, that happens due to moisture loss and moving water in and out of concrete. Salt scaling mechanisms are somewhat similar in the sense that de-icing salts increase the number of freeze-thaw cycles, which causes pressure to build up and local cracking and delaminations that can occur. In one sense, if you were to think about the different types of deterioration that we see in concrete structures, a lot of them are due to these expansive stresses that build up just across different scales. So, if you get corrosion products that form around the surface of a piece of reinforcing, those corrosion products, because they have a larger volume than the surrounding initial material, cause these expansive stresses that to occur. And a similar sort of phenomenon happens with freeze thaw as well, where you get water expansion within pores and causes cracking just at a different scale. What we studied within our project are what I'll generally classify here as just ductile concrete materials. And there have been a range of these that have been developed over the last 20 to 30 years. The most common, which a lot of people have heard of recently, is ultra high performance concrete. But there's others out there as well that different states and transportation agencies have looked at. In this project, we looked at a few different of these ductile concrete materials, where basically all of them exhibit some sort of either plastic or strain hardening response in direct tension. And each of these materials would come at a different cost. They might come with different resulting mechanical properties, different durability properties as well. In compression, they generally don't spall, so you have really good confinement that's provided on the compression side as well. And so the names of the three materials that we looked at were first ultra high performance concrete, which has very high compressive strength and mechanical strength or tensile strength as well. We looked at a system called engineered cementitious composites, which is denoted as ECC. And we also looked at a hybrid fiber reinforced concrete. And I'll explain what goes into each of these systems in a second. But the point here is that each of them kind of give you different levels of mechanical performance and durability performance as well. And they might suit the needs of a particular project in a different manner here. So to give you a sense of some of the benefits of using these materials, if we look at just a direct tension when these systems are reinforced, you get these really tight micro cracks that occur in these ductile concrete materials. So the figure on the left represents a traditional reinforced concrete system. And you see the large cracks that develop, and then you look at the system on the right, which is one of these ductile concrete materials, and you see multiple cracks that form, but they're all very fine. And that fine nature can lend itself to advantages on the durability side that are beyond what we might sort of expect or even need. And so while this gives us kind of potential improvements from a structural engineering perspective, it also gives us significant potential benefits on it from a durability related area as well. So the different systems that we looked at in this project, again, were ultra high performance concrete, engineered cementitious composites, and hybrid fiber reinforced concretes. The UHPC system had a very high binder content, did not use coarse aggregate, and used steel fibers at a volume percentage of 2% by volume. The engineered cementitious composite was a system that was developed primarily in Michigan from a professor there at University of Michigan named Professor Victor Lee. And the system that we looked at there used polymeric fibers. It also had a mortar matrix and had 2% by volume polymeric fibers. The particular polymer that we're working with were PVA fibers. And the last system that we looked at was called a hybrid fiber reinforced concrete. And this has mechanical properties that are probably closest to like a traditional concrete system in the sense that we're using coarse aggregate. And here this is called a hybrid system because it uses a hybridization of larger steel fibers and smaller polymeric fibers as well at a combined percentage of 2%. I think the steel fibers were at 1.8% and the polymeric fibers were at 0.2%. But this gives you a sense of the different systems that we were looking at. Within this project, we did a range of different experimental testing. The primary of which that we'll talk about today involves corrosion testing. So we used corrosion tests to benchmark the performance of these fiber reinforced systems. And effectively what we did is we took small reinforced beams made of these different systems, and we exposed them to a 3% sodium chloride solution. That sodium chloride solution was applied in a sort of a cyclic manner where we applied the solution, we then allowed it to dry, we reapplied the solution, allowed it to dry, et cetera. And it was kept in a constant relative humidity environment that was basically designed to move the chlorides through the system in a expeditious manner. And then in terms of like some of the things that we looked at changing like the concrete system that we have itself. So we looked at the different fiber reinforced concrete systems that I presented on the last slide. We looked at a few kind of standard New Jersey Department of Transportation systems as well. We also looked at the initial state of the system, whether it was pre-cracked or uncracked. And specifically what we're interested in is, if you were to get some initial cracking, whether it be from mechanical loading or shrinkage or whatever sort of effects that you might have in a real system, how does that influence the long-term durability? So if you get cracks in whether it be a traditional concrete or one of these new systems, how will that influence long-term corrosion? And we also looked at other reinforcing systems as well. Matt will also touch on some other tests that we did, specifically freeze thaw and some shrinkage testing, I think as well, to talk about sort of the range of different durability properties that we have in these systems. Some other areas of interest that we looked at were if you were to place one of these materials in a bridge deck. What would be the long-term durability performance with that? And the way that we did that was we used a numerical modeling system where we combined the effects of both mechanical cracking behavior as well as chloride ingress and corrosion as well. And we'll walk through that numerical simulation framework and some specific examples in here. So with that, I'm going to just pass the controls off to my colleague, and Matt Adams, and he'll be walking through the experimental program. Matt, let me just back up for you. Give me 1 second. There you go. That should work. You're muted, Matt. Yep.
Thank you. I think I'm unmuted now. Sorry, having the controls didn't give me access to the panel for some reason. So, like we said, I'm going to talk about our experimental program a bit. So we looked at a range of durability tests to sort of try to benchmark the difference between these 3 different materials and some existing mixtures that are used by NJDOT. So we looked at drying, shrinkage, freezing and thawing, and salt scaling of these systems. And then we also did a range of tests to look at the corrosion performance of these systems as well. So we did some accelerated corrosion testing through the ASTM G109 tests. We did chloride profiling to measure the coefficient of chloride diffusion in these systems. And then we also did the rapid chloride penetration test, which if you're familiar with this is a test. This is a quick test method that is used as a surrogate for how quickly salts can penetrate through the concrete to get to steel. However, it's well designed for ordinary concrete, but there are questions about its applicability for some of these more ductile systems. So we'll talk about all of these moving forward. For our concrete materials, we used 2 ordinary concrete systems, so a self-consolidating concrete and a high-performance concrete. These were both based off of some standard mixture designs that are used here in New Jersey. And then we also used the 3 ductile concrete systems, so the ECC, high FRC, and UHPC. We also looked at 5 different types of reinforcement materials in the G109 test. And then we also took a set of epoxy-coated reinforcement, and we pre-damaged them basically by breaking off a little bit of the epoxy coating to sort of simulate the performance of those materials in the field, where epoxy coated, while it works great when that epoxy stays on, is a little bit more prone to damage, and that can really impact the performance of it. So here are our results from this study. So first, I just want to talk about some of our fresh and hardened, or our hardened properties, and the air content. So as you can see, our strengths were all in relatively the same area for everything except for the UHPC. The UHPC was a bagged product that we got from Lafarge, and so this was the ductile material from Lafarge. And so that strength was up above 20,000 PSI, but everything else was in the 5,000 to 8,000 PSI range. And so you can really see the big difference in the compressive strength of those systems. The big thing I want to note here is, particularly for the HPC and SCCP, we had relatively low air contents. We really had trouble air entraining these mixtures in the lab. If any of you are familiar with labcrete versus field concrete, air entrainment is really a bear in the lab to get right. And unfortunately, this was done during COVID, and we should have switched to a different air entrainer to try to get better air entrainment, but procuring materials during the height of COVID was just, basically impossible most of the time. And so keep those air and contents in mind, because they do affect some of our results. And we hope to someday have a chance to rerun some of these tests for the freeze-thaw damage. So first, let's talk about drying shrinkage. So of course, drying shrinkage, you take a bar of concrete, you place it after curing into a drying environment and measure its length as it loses water, and that will give you an idea of the shrinkage. So in this system, in this test, the UHPC had the lowest shrinkage, while the high FRC and ECC both had the highest levels of shrinkage, and the ordinary concrete was in between. So what we can see here is that, really these ductile concretes do tend to have a little bit more shrinkage, except for the UHPC. But one thing to note is that even though those levels of shrinkage are higher, and that is generally due to the high cement contents, the test method that we used, ASTM C157, does not necessarily measure cracking propensity. It's just measuring free shrinkage. There's no restraint in the system. And other research has shown that these ductile concretes, while they do shrink a little bit more, they also tend to crack less because of the fiber content. And in this test method, the UHPC showed the lowest drying shrinkage. But this test method also doesn't capture autogenous shrinkage, which is typically a bigger shrinkage issue for UHPC than drying shrinkage is for UHPC. And that really needs to be captured earlier on. And this test method really allows those systems to cure for too long to capture that autogenous shrinkage. And so, basically what we can say is that the shrinkage results were
I found this on the
probably in the same area for these systems, and probably around the same cracking propensity. But of course, when you use those fibers, you'll hold everything together, so you could get less ingress. For freeze-thaw, our two systems that were ordinary concrete, the SCCP and the HPC, both failed fairly early on. But again, those systems, we had a lot of trouble getting air entraining in. So this makes sense. The air entrainment was really quite low for those. The high FRC also failed despite having 7.5% air content. And so that was that shows that high FRC may not be the best choice in freeze-thaw applications. And that may have to do with the certain type of systems that are in there, and the different fibers that are in there causing more expansion during that freeze-thaw, maybe allowing water to get into places that doesn't have access to the air entrainment. So more research really needs to be done to understand why those systems, why that high FRC system performed that way. But we do see that the ECC and UHPC, both with moderate levels of air entrainment, only 5%, both performed really well. And so we can see these are what the specimens looked like at the end of testing. The UHPC and the ECC basically look completely undamaged. And so they performed really, really quite well in freeze-thaw testing. So what we know is that our ordinary concrete was difficult to air entrain. Likely these results show that you don't get enough air entrainment in there, you're definitely not going to get good freeze-thaw performance. Even though that high FRC did perform poorly. So we need to take a look at that a little bit more, but some encouraging results with the ECC and UHPC. Salt scaling is the third of the non-corrosion durability tests we looked at. And for this test method, you take a concrete slab, a small concrete slab, and you put a dam around it, and you pond it with a chloride solution. And then this is more of a qualitative test. You look at the damage to the surface over time to determine its resistance to salt scaling. And so what we saw was that the SCCP and the high FRC both had the worst performance in terms of salt scaling. The HPC, ECC both had around a rating of 1, which is good, and the UHPC had essentially no damage noticed on it. Here's what the different samples look like over time. And so you can see once we get out to 50 cycles, so 50 cycles means you've put those chlorides on there and you've actually frozen it and thawed it for 50 times with that ponding on there. And so you can start to see that surface damage build up. And particularly on the normal concrete, you typically get those pocks in the surface. That's very standard damage with salt scaling. But one thing we noticed with the systems that had fibers is that the fibers tended to hold material on the surface. And so the test method doesn't actually request that you brush the surface or clean the surface off. You're just supposed to sort of rinse the waste material off and then look at the surface. However, that doesn't really give you a full picture of the damage that you're seeing in those slabs. And so we recommend that if you are testing these fiber reinforced systems in salt scaling, that you do a light wire brushing of the surface to try to clean off some of those materials that are stuck on with the fibers, because they may actually be a trip or a skid hazard, particularly for walkers, if they're stuck on there but not really tightly held on there. And then on the ECC system, we actually noticed a slightly different type of damage. Instead of small pocks, we got sort of larger delaminations. And this is likely due to the density of the fibers that are in that system, sort of holding those surface pieces together. And so you get thin delaminations across a larger area rather than small individual pocks coming off. So takeaways of our durability testing, really UHPC across the board for the durability testing had the best performance. In general, the ductile concrete systems had improved durability, though the high FRC was a little bit questionable. And we have some testing method modifications that need to be considered when we're looking at these ductile fiber reinforced systems. So next, I want to get into the corrosion testing. So one of the first things we started running were these G109 corrosion tests, and Matt talked about this a little bit, but this is essentially an accelerated corrosion test where you apply a dam up at the top of a reinforced prism. In that dam, you have a chloride solution that you put on for 2 weeks at a time, allowing it to stay wet and then drying it. And this helps to accelerate the rate at which those chlorides move into the system. And then we measure the corrosion current density of along the rebar, and that will tell us when corrosion has likely occurred. So the normal test method does not have you apply any preloading to develop cracks. However, with these ductile systems, you often, and even with the normal concrete, you actually often don't see any damage. And you'll see from our results in a year, even 2 years or 3 years time. And so to try to accelerate that and really show some more likely field situations where you do have some initial pre-cracking, either from loading or shrinkage of some sort, we looked at a modified version where we pre-cracked the systems. So we also looked at this across all 5 of our concrete mixtures, and then across our different rebar types, including some of the damaged epoxy coated rebar. And then some of our systems, all of our systems we did in an uncracked state, and some of them we did in a cracked state as well, to sort of examine that role of cracking. So what we noticed really is across the board on our uncracked specimens up to 700 days, so about 2 years, we have not seen corrosion begin on any of these samples. So we're still monitoring these. These are still in the lab, but this is why this test method tends to be a little bit slower. It certainly was longer than the project before we're going to see anything. So this is why it was important for us to look at some cracked specimens. We do see some corrosion in the fibers, the metal fibers at the surface. This is typical. However, this doesn't necessarily mean that corrosion has moved through the system. These are just fibers that were already exposed at the surface. And then these are our systems after we cracked. And so you can see for the HPC system, we get one large crack, whereas for the ductile concretes, we tend to get more distributed cracking pattern and smaller cracks. What we see here is above that red line typically means that corrosion may have occurred. So that dashed red line, if our corrosion current density is above that, that means that corrosion is likely to have started. The only system that we started to see corrosion in our cracked beams out to 700 days was the high FRC system. We actually had to stop that test just after 500 days. But we did see that corrosion was likely to have started in the high FRC system. But even our HPC system, the normal concrete, which is a standard mix used by the New Jersey DOT, is performing quite well in terms of corrosion performance. What we see here is that in particular, we had one of the three specimens that had a higher corrosion density than the other two. And this was the one with the largest crack in it as well. We also see some higher corrosion density early on. This is an artifact of the test method. As the system saturates with water over time, that early age, you tend to see some higher corrosion density. But what we're really concerned with is the long-term corrosion density. Our alternative reinforcements, we see that, again, the high FRC, even with the Chromex, had a corrosion density above the limit there. So likely even that Chromex was starting to corrode. Again, that was a system with a fairly large crack. But in our other cracked beams with alternative reinforcement, we still weren't seeing any corrosion. Our galvanized systems with the HPC, again, no corrosion happening there. And so in general, all of these systems performed well in corrosion. And the takeaway from this is really that you don't need to go to a UHPC system for good corrosion protection for a standard system, particularly if you're looking for not those iconic bridge 150-year service lives. We also did some chloride profile measurements. And again, you can see basically what this is showing us is the depth of the concrete along the x-axis and the amount of chloride by mass of concrete along the y-axis. And so as you go deeper, you tend to get less chloride in that system because it takes longer for those chlorides to get down to that system. So this was done at a year of ponding in that G109 test. We see with the UHPC system, of course, those chlorides got basically nowhere. There was a little bit on the surface, but once you get about 2 millimeters deep or 3 millimeters deep, we had no chlorides. The ECC system had a much higher chloride rate early on, but it quickly dives off. Our rebar was at 25 millimeters. So really only the high FRC was close to having measurable chlorides at that level. So really all of these systems were performing well, though for bang for your buck, really the HPC and the high FRC were or the ECC were performing the best in terms of the depth where we had our rebar. The UHPC, again, performed the best, but is also quite a bit more expensive. One thing we wanted to take a look at is the rapid chloride penetration test. So as I mentioned, this is a test that's often used because it's quick. And typically what we look at is the amount of charge that gets passed across a concrete sample, and that will tell us that's related to how likely it is that chlorides will move through that system in a way to cause corrosion. So once you're getting above about 2,000 coulombs passed, that's when you really need to start worrying about corrosion possibly happening in your system at an early age. So one thing that we looked at was whether using the fibers in these mixtures would impact the test method. Because remember, this test method is not actually passing chlorides through the system, it's just passing charge. Electrons are much smaller than full chloride ions, and so it's just a surrogate test, it's not an exact measurement. And so while it's been established, that relationship has been established quite well with ordinary concrete, so it's a great test to use on that HPC and SCCP mixtures. For our systems with fibers, it may not actually work well. And also the system in there is also the cementitious microstructural system is different. So what we do see is that our systems with fibers, particularly the ECC, had a fairly high charge passed with the fibers, and even with the UHPC, we do see about 10 times the charge passed than when we didn't have fibers in that. The high FRC system, which has metal fibers in it as well, actually we couldn't get a read on it because it was passing so much charge through that network of metal fibers. And so with the high FRC, you absolutely cannot use this test method for measuring that the chloride performance of that with the fibers in it. However, both the ECC and high FRC both showed fairly high charges passed, so above 2,000 coulombs, but that doesn't match really well with our profiling testing and our G109 testing. So it's pretty clear that the RCPT test is not really a great measure of chloride performance with these ductile concrete systems. So really more understanding to recalibrate that test method needs to be done. And here you can see that high FRC system that we did with the fibers still installed, and you can see those fibers have basically corroded in that test method, and that test method is only about 6 hours long. It started to corrode them immediately, and we basically had to stop the test after a few seconds because so much charge was being passed in that system. So in general, we did see the same trends, but the fibers can have an impact, and we really need to understand those systems long-term to get more information on how RCPT can be used. So I'll pass it back to Matt Bandelt to talk about the numerical framework. Thank you.
Thanks, Matt. So the last thing that we did as part of this project was developed a numerical framework to try to simulate some of the long-term behavior that we might see with some of these systems. Basically, there's two ways to evaluate service life, right? So there's an experimental way, which is, some of the things that Matt just talked about. And when we use experimental methods, we can get accurate results. They're fairly intuitive. You can figure out, why did something go wrong? What might be the cause, et cetera. And then there's numerical framework as well. So here I'm just showing like a structural test on the top of something that was physically tested versus numerically simulated. And a numerical simulation has advantages and disadvantages. So it's cost efficient. So, we don't have to actually procure the materials that we're using. It's time efficient. Once we have a simulation that's set up, we can sort of simulate whether it be mechanical loading or durability conditioning in a much smaller time frame. And it's also easily extended to various scenarios. So, we can move loads around. We can think about different boundary conditions for, say, temperature cycling or chloride exposure or whatever it might be. But there's some gaps in current numerical modeling. So oftentimes our numerical methods don't include the effects of cracking. And here I'm particularly talking about simulating deterioration. Often that's done where we don't consider the effects of cracking. Sometimes we don't simulate boundary conditions properly, or they're not updated on a regular basis. One thing that we would like to be able to do with numerical methods is combine the effects of mechanical loading and being able to simulate, say, corrosion behavior or some other phenomenon. And oftentimes the big gap here is that oftentimes the structural deterioration is not coupled with the environmental conditioning and the resulting deterioration that we see. And so what we set out to do was basically combine these sorts of things and develop a framework that allowed us to simulate both mechanical damage and durability damage in a combined framework. And we applied it specifically to one type of material and looked at a case study example so that you could see what might be the long-term performance of a bridge deck made of two different types of systems. So, once again, testing and simulation standards often sort of treat each form of damage in isolation. So for example, we often think of, there's a truck that drives over, a bridge deck, and maybe over a long time, you get some fatigue cracking or whatever it might be. And then we think of corrosion mechanisms or freeze-thaw or whatever durability issue we might have, and we think of that as another sort of isolated manner. But we know that there's this coupling that happens, and Matt went through some of the chloride profiles of crack specimens, right? And what you could see was, in the crack specimens, we showed that there was the propensity for some of this corrosion to potentially occur, whereas in uncracked specimens in the same time frame, we never saw that. And so the benefits of some of these new concrete materials might be more apparent when we study like the coupled forms of deterioration. And we also have to sort of just think about the fact that boundary conditions are time dependent and not stationary. And so what we did is once again, we set out to develop this numerical framework that would allow us to think about some of these things in a holistic manner, so that we could get a sense of how might things or what might be the behavior that we see in a time frame that we can't necessarily simulate within a 2 to 3 year funded research project in an experimental laboratory. And so we use numerical tools to help us with that. And so we developed a modeling framework where we considered the initial structural status. We coupled material ingress with damage conditions. It was time dependent, and so parameters were updated at each time step. And then we connected all stages in the corrosion process. And so through this, what we did is we sort of went through and looked at structural response, material ingress, and then the electrochemical reactions as well. And so this involved basically using 3 pieces of software to do this. So we used a structural mechanics software that we use in our research group called Diana. It's similar to ANSYS or Abacus or any other structural mechanics piece of software. The reason why we use it is because it has really good concrete mechanical material models that allow us to simulate damage quite nicely. We then basically what we did is, if we were to say load something up, and then we wanted to go and simulate, what is the chloride penetration that's happening at some particular time. We used MATLAB to connect our Diana software to a program called COMSOL. And this COMSOL software, it does multi-physics modeling that allows us to simulate the chloride ingress. And basically that requires some input parameters, such as chloride diffusion coefficients, that we took from our experimental testing. And then based on the chloride diffusion that we have, we can then figure out, has depassivation occurred? If so, are we going to go into a corrosion analysis? And then that corrosion analysis, when corrosion products form, those products caused volume expansion, which then leads to cracking. And so what we were able to do was basically link these pieces of software and simulate a fully time-dependent behavior from sort of initial structural mechanics to chloride penetration to corrosion analysis, which causes expansion, and then additional cracking, et cetera. And we were able to look at the time-dependent behavior of different samples. And so these were the main steps, structural analysis, chloride ingress analysis, corrosion analysis, and then simulating the rust expansion calculation and repeating this over time. And so what we did is we took a representative bridge deck, and we made comparisons of a bridge deck that was made of traditional reinforced concrete materials and made of UHPC. And when we did this, we took in mechanical properties and durability properties as our input parameters that were developed or that were found from both experimental testing that we did in some of the results that Matt showed, but we were able to do is simulate it over a much longer time frame than what we could simulate in our laboratory conditions. And we tried to subject that to realistic environmental conditions in New Jersey. And so we had a chloride source, which was from de-icing salts, and we looked at temperature variations. New Jersey has a relatively constant humidity as compared to other environments, especially compared to what we could sort of simulate in the laboratory. And so what we did is we looked at, or what we applied to our computational model were these simulations of basically chloride exposure in certain months, and then temperature swings over the course of a year. And we repeated this for basically decades long in our computer model to simulate how long it might take to see chlorides at different thresholds, or what the corrosion might look like at different points in time. So what we have here is basically a bridge deck. We're modeling a small portion of it. We apply some loads to it. And the main thing to note here is that our concrete, we basically assumed a larger thickness than what we would have for a UHPC, or what I could say it the inverse way, in that if we were using one of these UHPC solutions, we might might be able to take advantage of its high mechanical properties and use a smaller section thickness to result in equivalent strength. And so that's what we did. We designed these to have equivalent strengths. They'll wind up having different stiffnesses because you have different thicknesses, but the strengths were the same. And what we did is we exposed them to some mechanical loading. And what we sort of went through was we loaded it up to, this is a simulation of the load displacement behavior of the reinforced concrete and reinforced UHPC. And we loaded it up to basically get us to a representative service load. And so we took it to be the same applied external load. And our reinforced concrete, the crack width that we had at that point was 0.2 millimeters, whereas with the UHPC, it was about 1/10 the size, despite having the smaller section thickness and the smaller amount of cover as well. And what I'll show you here is just some results of this combined mechanical and environmental conditioning simulation framework. And so after 30 years of de-icing exposure, here are some of the results that we see. So on the left-hand side, what we can look at is two different cracking patterns. The main thing to look at here is that basically as you move from blue to red in the ones that say cracking, you're getting more principal tensile strains, which is indicative of basically more cracking. And so you see these larger cracks that form in the reinforced concrete near the boundary conditions, as opposed to the UHPC. The other thing we can look at in figure B and D are the chloride levels that we see in the different systems. And so what you see after 30 years of exposure is significantly higher chlorides in the reinforced concrete member as compared to the UHPC, despite having additionally the smaller depth. And so much like we looked at chloride at various depths from our experimental specimens about 20 minutes ago, we can simulate the same sorts of things in a representative bridge deck and look at, basically how much chloride might we expect, an inch down into a member in one of these UHPC systems versus a concrete after 30 years of exposure. And so this gives you a sense of sort of the level of cracking that we see at two different time periods. So, let's take a look at time 30 years for reinforced concrete versus time 80 years in the UHPC, and just see much less damage in these ultra high performance systems, which is sort of what you might expect given the higher upfront cost. But this potentially provides some significant advantages to systems that we want to last a very long time or require very little maintenance over its service life. We also looked at a condition rating system to look at the condition rating at different time periods. And this figure isn't showing correctly, but the reinforced concrete was at a condition rating of basically 79, whereas the UHPC was up in the 90s. So it had only deteriorated, about 8%, whereas the reinforced concrete deteriorated significantly more. So some takeaways from the numerical modeling framework. First, the multi-physics sort of numerical approach gives us an effective way in predicting service life evaluations. The UHPC bridge deck had slower deterioration, and a companion study that our colleague Hao Wang helped us with, that we didn't get into the results here, showed that when you look at actual dollars to it, UHPC was a cost-effective solution compared to the RC system in a 50-year service life. And that was, it's in our actual technical report, but not within this presentation, just due to the time constraints. So now what I'll do is I'll summarize with some conclusions and things that we sort of hope to work on in the future based on this study. So in general, UHPC had the best durability performance that we saw of all the ductile concrete systems. Now, that's somewhat to be expected given the high upfront cost and the high mechanical properties that we have as well. In some of the fiber reinforced systems, there's high cementitious material content, and that resulted in increased drying shrinkage. But those fibers helped improve durability performance across a range of different metrics. And we obviously saw a direct relationship between corrosion intensity and crack width in the ductile concrete systems. So another big thing that we sort of came out of this study looking at was just some of the considerations that one must take when using some of these newer concrete materials and the test methods that go along with them. So for example, we saw how the fibers influenced RCPT results, and why those might not be the best test method. Matt had also gone into some issues with salt scaling, et cetera. And our multi-physics numerical approach gave us some interesting information on service life performance as well. So there's lots of different sort of recommendations that we have. So in terms of testing corrosion behavior in these ductile concrete systems, looking at specimen size, changing the cracking method, brine solution, cover depth, different ways to measure, et cetera. These are all things that we think should be considered when evaluating these systems. With looking at the salt scaling tests, and you're using these ductile fiber reinforced concretes, thinking about surface finishing and surface evaluation and what rating criteria should be used is definitely something to consider as well. In terms of future work, there's some ideas that we have regarding RCPT results and how those should be interpreted in the ductile concrete systems. Should we consider cracking or not, or just in its initial state? Salt scaling is another issue with the ductile concrete systems, and how you properly sort of prepare the specimens, and then investigating the applicability of resistivity testing in these ductile concrete systems. So with that, I'll sort of stop there in terms of our presentation. We're right at the time we wanted to be at, and I'll stop sharing as well. And I'll turn it back to you so that you can pose us some questions.
Thank you so much for the presentation, guys. That was wonderful. We do have quite a few questions, and I'm going to start at the ones that came in earliest. So some of these were related to what was on the screen at the time. We might have to do a little bit of detective work to find out exactly what the reference was to, but we'll start with the first one. UHPC seems to be advancing in the bridge industry. What are the biggest challenges for UHPC moving forward on the rehabilitation of bridge decks, for example?
Yeah, I'll start on this one, I guess. So yes, it's it's advancing quite rapidly. I don't have the figure in this presentation, but if you the FHWA has a website where you can go and see all the projects where UHPC has been deployed, and well, not all the projects, but a lot of the projects that they've been involved with. And if you plot the number of projects over time, what you see is an exponential growth curve. And that's a great thing, you know, for the construction industry to see new materials being adopted at an increasing rate. And, you know, part of that is due to the fact that there's been a lot of research that's gone on. There's a lot more standards that are coming out in terms of testing. So there's recently after this project ended, AASHTO has an approved test method to quantify the tensile properties of UHPC. There's design specifications that are coming out and being validated by AASHTO. There's one was actually recently approved. ACI is moving in directions to help develop sort of design guidance with using these materials. And so the short answer to it is I think the biggest challenge is getting new people people to get familiar and comfortable with using these design methods, sort of conducting the tests as they need to be conducted, thinking about the considerations. As we move past some of that, I think that exponential growth curve that I was talking about before will just continue in leaps and bounds to grow. And I'll say that with a caveat that, you know, it's not some of these systems, whether it be UHPC or others, are not going to be the right solution for necessarily every single project. You know, you don't need to make sidewalk concrete out of something that's, you know, significantly higher cost, right? But on things that we want to last, you know, 100 years or 150 years, or things that we want to be able to build very quickly, you know, that's where some of these systems might be super appropriate. And Matt, I don't know if you have anything else to add on that.
No, you summed that up pretty good.
Okay.
Great. Just to stick on UHPC, can you please touch on UHPC fire resistance?
That's something I know very, very little about. I know that there's a researcher, I think at Michigan State University, who's done some research in this, but I know, you know, I honestly couldn't give you much technical information on it. So I don't want to speak incorrectly.
Sure. And regarding the resiliency of concrete, are advanced reinforced concrete materials more capable of handling complex freeze-thaw cycles that could be outcomes of climate change? And if so, do you have any modeling projections on how regular, ordinary concrete fares to the advanced materials? And this is for either of you, obviously.
Yeah, I'll take this. So, you know, we haven't done any modeling looking at, you know, the difference between sort of the standard idea of freeze-thaw cycles versus what's coming from climate change. But in general, these systems are more resilient. They just perform better. So as you saw from the freeze-thaw testing, after 300 cycles, we really saw zero damage in that UHPC system. And the ECC system performed quite well as well. And so, you know, when you see that level of performance in these accelerated tests, which are often very aggressive, you can sort of extrapolate that these will perform well or perform better in a more aggressive environment. And so part of our work on the research end is trying to understand if the way we've calibrated these test methods, so say for freeze-thaw, we look at amount of damage after 300 cycles. Is that sufficient moving forward? Are 300 cycles enough, or is the limit that we set for damage? Do we need to increase that? Those are all things that, you know, our field is looking at and considering. But really, you know, you can see now that those UHPC systems in particular just, you know, can handle more damage. So yeah,
right. Why did the high FRC show much higher free shrinkage than HPC? High FRC mixed design is different. Go ahead.
Sorry, yeah. So, so the mixed design of the high FRC is slightly different from the other ones. All of these three, ECC, high FRC, UHPC, all have different mixed designs. One thing in particular with the high FRC, even though it's got those blended fibers, is that it also has a significantly higher water to cement ratio. So you're looking at like a 0.45 water to cement ratio in a high FRC, whereas for an ECC and UHPC, you're looking at 0.32 for the ECC and even lower for the UHPC. And so the high FRC, because it's got more water, it's weaker, it's a little bit more prone to drying shrinkage, whereas the other two systems they just don't have the water in them that is going to leave during free shrinkage. The microstructure is also tighter, so water that's in there has a lot more trouble getting out, but they do tend to have more associated autogenous shrinkage, so that really early age shrinkage where it's self-desiccating from the interior as it's hydrating the cement. So there's a bit of a trade-off there with those two. With UHPC, that tends to be less of a concern because it's stronger, so it can resist those shrinkage stresses. But that's why we're seeing that higher shrinkage with high FRC, is it just has a higher water content in there.
And could your modeling adjust relative humidity to a more wet and hot climate in the future?
Yes, absolutely. Yeah. So the framework, the case study that we looked at was in particular in New Jersey, but we could modify that to be kind of in any setting. Absolutely. So you can see where it geographically might be more advantageous to use certain systems.
Sure. We also had a question here. Can you explain more about the deterioration that you showed in slide 66?
Sure. So
Maybe bring that up and we can take a look.
Sure. So I think this. Can you see my screen, Matt?
Yes.
Okay. Okay. So basically, what we did was, and I don't recall exactly what these particular values referred to, but so what we looked at were basically principal tensile strains throughout a bridge area. So here, like if we look at the section of bridge that we were looking at, and you see these colors coincide with basically different levels of principal tensile strain. So red being a higher principal tensile strain, blue being the smallest principal tensile strain. And what we did is we counted up areas that were in different sections. So like blue and light blue, green and light green, yellow, red, et cetera. And based on the percent area that we saw in our section that was kind of severely damaged or like slightly damaged or had no damage at all, it would get, that area would get multiplied by basically a 0% for severe, 40% for something that was in a poor category, 70% that was something in fair, et cetera. And this was a method that was effectively proposed by Pat Zari and Andres Rhoda. But we did this in a numerical framework as opposed to kind of counting area that you might see on an actual bridge deck. And for the reinforced concrete, what we saw was a rating of 79.1% after 30 years, whereas the UHPC was above 90% after an 80-year time frame. So hopefully that answers a little bit of the sort of the method that was used.
Mm-hmm. Do you guys have any experience in HPIC and how it compares to UHPC and HPC?
High performance internal curing, I assume, is what Ali's referring there. Matt, do you have any comments on internal curing? And
yeah, so in internal curing, I would say that it's a slightly different category than UHPC and HPC. UHPC and HPC tend to refer to really it's a strength category that then filters down into all sorts of other aspects. The internal curing, whether it's used in HPC or UHPC, is just going to help the system. It makes sure that there's water provided to help reduce any shrinkage that does occur, whether it's from autogenous or drying shrinkage. And it sort of helps develop that microstructure and ensure that you're reaching the strength that you intend to reach. So if you have well implemented internal curing, it essentially will make your UHPC or your HPC better. But like all things that we work with in concrete, when done correctly, it should improve everything. But if it's not done correctly, it can make things drastically worse. So, it would have a similar effect on both mixtures if it's done correctly by helping just to provide water to prevent, closure of pores or lack of water access for curing. So it should have a similar effect on both systems.
Would you say that HPC is the best choice, even though it's prone to cracks?
Yeah, I see this comment. We use HPC in all NJDOT bridge deck construction. Do you guys think HPC is the best choice, even though it's prone to bridge deck? So I'll sort of avoid directly answering that question, and instead what I'll say in some of the really unique situations where I've seen UHPC used, so for example, like the Delaware Memorial Bridge, right? So they're doing this large overlay of UHPC, and I think that's a really great setting to use it in an overlay setting, because as you saw in some of the results that Matt presented experimentally, basically, within 2 or 3 millimeters, there was no chlorides whatsoever after 2 years of this accelerated experimental program with the UHPC system. Whereas you saw, down to say 20 millimeters, so almost 10 times as much depth, there were pretty measurable chlorides in this 2-year time frame. In the simulations, we saw similar things, so much higher time to get anywhere close to the level of chlorides. And so I think using in like overlay settings where maybe you don't use quite as much of these materials is like a really kind of good spot where they could be used, or in locations where you maybe you want to make a connection from something that's precast. UHPC makes sense. So I think there's locations where any one of these materials might be great to be used. And I think thinking about the quantity that you need, its cost, what are the potential trade-offs is kind of how to go about it. I don't know if you have anything else to add, Matt.
Yeah, I mean, part of it too is just use planning. If you're really looking to have a bridge stick around for 100+ years, and you really know that it's not going to get modified for other reasons in that time, then UHPC could be the right choice for that. Whereas a lot of times our infrastructure has to be replaced or changed or modified due to other reasons, even than just that it's not performing or it's deteriorated. So trying to understand that a little bit better helps understand whether UHPC is the right product or not. But like Matt said, there are ways that you can use UHPC sort of judiciously so as to keep that cost premium down while also getting those those better performance aspects.
Thank you for navigating that question. I think we'll go to the last one. How much was the higher steel fiber volume content, and did you use the GeoCore 8 testing device?
So I'm not sure what that particular testing device is, but the fiber content that we were working with in this study was 2%. Generally speaking, most of these systems use somewhere in the range of 1% to 2% to get the high performing type behavior. And what I mean by that is getting like a plastic type response or what we would call pseudo strain hardening and direct tension. So that generally that requires 1% to 2% by volume. The lower content you get, it's not really going to affect your tensile strength, but it will affect the sort of level of cracking you can get before you get some sort of localization that occurs.
Yeah, so the G-Core system is really for field testing of corrosion rate. We're able to set up in our lab samples that are all wired, so we can get direct current measurements a lot easier than with some of these field systems that are best used out in the field. And so we didn't have to use a system like the G-Core.
All right, well, thank you very much, guys. I think that's the end of it for questions.
Yep.
We appreciate the presentation. Before bringing this event to a close, I wanted to thank our speakers for both their presentations and also thank all our attendees for their interest in attending today and for their questions. Today's presentations and a recording of the event will be posted on the NJDOT Technology Transfer website, and we're going to send out a notice to everybody who registered when those presentations have been posted and how to access the certificate for continuing education credits. Please be sure to fill out and submit the feedback survey for today's event. It should be available to fill out once the webinar is closed. Thank you so much again to our presenters, and stay safe, everybody.
Thank you. Bye-bye.
Thank you, everybody.
Thank you.